So the topic of my talk today will be fairly straightforward. I want to present essentially a type natural deduction system for reasoning if the judgments there exist a proof of phi, and which I will call existential judgments. More specifically, I will introduce this type natural deductions in two variants. The first one, which I will call X, will be purely logical one. We're dealing with judgments of the form phi. It's just true or true without sort of the explicit proof terms. And then later on, I'll introduce its computational variant, which I call Lex plus, which will deal with explicit proof terms and also initially be equipped with equivalence or equality in the language itself. Some key features of the systems to be presented. First, I'll be following the general methodology of Martin-Löf by distinguishing between judgments and propositions. This was probably already obvious from the first slide. Furthermore, what's interesting, these existential judgments that will be sort of the main object for the natural deduction systems can be then internalized into sort of proof existence modality, which shall be denoted by this sort of inverted triangle. So, in effect, what we'll be dealing with is essentially sort of type theory or model type theory with constructive undertones. And last but not least, sort of the notion of existence that I'll be presupposing and working with is distinct than the one to associate, for example, with the existential quantifier. This is mainly sort of the consequence of taking the Martin-Löfian approach towards this, because essentially the existential judgments are in a way conceptually preceding formation of any propositions, even the existential ones. So these are sort of the more basic notions in the sort of ground framework to be presented. Furthermore, at the outset, I'll be talking about the relation of these two variants, the Lex and Lex plus, to similar or related modalities. Mainly, I'll focus on two modalities. The first is truncation modality, most often associated with homotopy type theory. And then we also talk briefly of the relation of this existence modality, the triangle, to Lex modality. And more specifically, we'll show that actually one sort of a specific variant of the Lex system is equivalent to one concrete Lex logic, specifically the one developed by Fenwick and Davies, that if we extend the Lex logic by the axiom on the screen, but more of that later, and we'll talk about what is specifically the sort of the natural interpretation of this axiom is to be and how it's related to the notion of proof irrelevance. So this would be the general sort of characteristics of the systems we'll be talking about. Now let's talk about sort of motivation, why even bother with this. So generally speaking, in the sort of the framework of constructive or intuitionistic tradition, we can generally speaking identify two closely related, but in a way distinct notions of proposition phi being true. The first one, I call it just phi being true and mark it with 1, meaning that we can say the proposition phi is true if we have a proof, some concrete proof A. So we have it at hand, we know its structure, we know how it looks like, the proposition phi. So this is the first sense. In the second sense, it's in a way sufficient to say the proposition phi is true if just there exists a proof of phi. We don't actually need to sort of have it at hand ready, know its structure, sort of understand in a way how it necessarily works. It's just proposition is true when there's a proof of it. We don't necessarily have it sort of ready at hand. Now, these two different notions of proposition being true can be essentially linked to two different traditions that to be identified in generally the area of constructive reasoning, let's say. The first one, so the proof-relevant approaches, which can be characterized as that proofs are really treated as sort of proper mathematical objects. It's not enough to know that, for example, if some proposition is true. What's also important is that we have to know what its proof looks like. In practice, what this means essentially that we can have different proofs, non-equivalent proofs for one and the same proposition. In contradistinction to this, there are, of course, the opposite of that. This is sort of a proof-irrelevant approaches. And here the proofs are really treated only as a sort of means to an end. Proofs are, well, not necessarily treated as a proper mathematical objects, but what's important is that it's sufficient to know that the proof exists, and so it makes some sort of proposition true, but we don't really care beyond the fact that the proof exists. So they don't really matter what's its structure, what it looks like, whether it's equal to some other proof, and so on. So what this again means in practice for us, when we apply it, means that, for example, any two proofs for the same proposition will be regarded as equivalent. This is known as sort of the proposition proof irrelevance, or PIP for short. This pretty much goes back to, I think, the Bruin was first who sort of introduced this notion in the 70s. And again, the idea is generally that if it's proposition, like we don't care about its proof, let's sort of render them all equivalent. Now, so if we return to the first two notions of being true, and sort of at this additional interpretation, we can sort of informally put the following equivalences. We can say that the phi true in the first sense essentially means that the phi is proof relevantly true, and shall be using the notation just phi true, which means phi is proof that phi is true, and we sort of care about the proofs. And the phi being true in the second sense, then pretty much corresponds to the idea that the phi is proof relevant true. I'll be using the sort of shorthanded notation that I'll say that phi is just true, like we don't care about the proofs themselves, it's that their existence is sufficient for us. Now, what's interesting is that in the sort of type theoretical setting, the right-hand side of the first equivalence is typically formalized as the sort of typing judgment, so A colon phi. So the idea that if we have a proof A of P, this sort of meta-language informal talk, is typically captured inside the type theories via this typing judgments. Again, this is pretty much ever present in all the basic modern dependent or non-dependent type theories, utilizing in some form or another Cary-Howard correspondence. Going again from Martin-Löf's constructive theory, calculus of construction by concrete word, the unified theory of dependent types by Luo, and the already also mentioned homotopy type theory. So this is really sort of one of the basic stones of the formalisms itself for type theories. However, the sort of the right-hand side of the phi being true in the second sense is effectively absent. But this means that there are, at least to my knowledge, there are no type theories expertly working with the basic judgments. That's important, corresponding to the idea that there exists a proof of phi. Meaning, it seems to be prevalently preferring the proof relevant notion of truth for obvious reasons. And to this sort of circles back to the initial portion of my talk. The purpose of this talk will be essentially to find out what we can put instead of the question mark, meaning we'll try to present two systems that deal with basic judgments that are capable of capturing this proof irrelevant notion of truth. So let's start with looking at the first one, the logical variant. Some brief overview of the language itself. So as we can see, it'll be essentially just two logical connectives, implication and existence modality. It's mainly for just simplicity's sake and sufficient to sort of demonstrate all the key principles at play. Then we can form context. Just a side note, should probably already familiar for this, but we'll be using the natural deduction in sort of the segment style. And of course, we have two categorical judgments, which sort of the one of the main distinctions from the standard, let's say, type natural deduction systems or type theoretical frameworks. There is only the basic phi is true. We add additional one, the phi is just true, meaning that we don't really care about the structure of its proof. From these two categorical judgments, we can, of course, then form hypothetical judgments. This is pretty much business as usual. Now let's take a brief look at the rules of the system. The first are the hypothetical rule for making assumptions. This is pretty much basic, nothing interesting there. The first interesting is the just rule that essentially says that if we know that phi is true, we can also derive that phi is just true, meaning that if we essentially care about the structure of the proof, we can always choose to, in a way, like forget the structure of the proof, like stop caring. So this is essentially how we define the meaning of the judgment just true. Of course, the other direction doesn't work because once you sort of decide that you don't care about the structure, you cannot suddenly just start caring about it and turn it into the phi true. So it's sort of irreversible in a way process. So when you sort of step from the relevant domain into the proof relevant, there's no way back, with some minor exceptions as we'll see a little bit later. Now, there's the introduction and elimination rules for the two connectives. Here I'm using the sort of star meta variable. So to simplify the idea that we can sort of switch between either if we care about the true variance or the just true variance. So it will be probably easier if we just sort of just substitute for the meta variable and go through it through there. So now we substitute the meta variable star with true. So again, no change in the hypothesis forming rule, and the just rule stays the same. Now let's take a look at the introduction rules for implication and its elimination rule. This is pretty much standard rule as you would find in literature. Nothing peculiar is happening here. So let's move on to the sort of the new modality, the existence modality, which is the much more interesting part of the system. So first, let's take a look at the introduction rule. As you notice that what's actually the premise is that the phi has to be just true. So in a way, this allows us to, as I mentioned, that there's the possibility to internalize the sort of the proof irrelevant judgments into the sort of the logical part of the system. So we can, if we know that phi is just true, we can internalize this idea via the triangle modality by forming a sort of new judgment that is now true. But it tells us that in a way we don't care about the structure of the phi because we now apply the modality. So this is how to introduce the modality. Then the elimination rule effectively tells us how to get rid of it. Again, here, what's the most interesting part about this is notice that essentially the conclusions, both at the hypothetical premise, on the right-hand side, and the conclusions are restricted only to just true judgments. Meaning, if you want to eliminate the triangle phi true judgment, you can, for the, let's say, for the sake of the argument, assume that actually it's just true, not just, let's say, only true, in the sense that you can assume it, and then you are free to sort of derive whatever you want from it, but only as long as it's still only just true. So for the for the purposes of eliminating, you can in a way peek behind the sort of forgotten structure of the proof and in a way pretend as if it's still available, because there's just assumption and we are quite close, but I'll get to it. But for the purposes, you just assume, you sort of peek behind the modality and to look at the structure, so you can apply selectors for it and similar, but only you're still restricted that whatever you get from it, you still have to sort of hide it back behind the sort of the forgotten box about the structure. It was captured by the just true statement. So it's sort of restricted. What can you get back from it and how to eliminate it? Now, just to show you, we would look the variant with just true. Again, nothing too unexpected happens here. Just I'll be skipping a little bit forward, but it's good to know that, for example, the elimination rule was this sort of the J variants for the proof irrelevant cases. The introduction and elimination rule for the triangle modality can be actually in a way derived from the standard non-J variants of the introduction and elimination rules for the triangle modality. But it's not the case, for example, from the introduction implication introduction rule in this J variant. That happens something sort of quite distinct from other previous frameworks. But I will get to that more in detail later. But now just sort of mention that even though this might seem like sort of just another variant, like it's true or just true, it doesn't really happening something crucial underneath the system. It really adds some new sort of expressive power to the system, which mainly stands behind this introduction rule for implication in this just true variant. So we need this as well. Now, since in this purely logical variant of the system, we don't actually have some sort of equality on the sort of object language. So far, we'll capture this the sort of the proof irrelevance principle, the big principle. We have the sort of meta-level statement as follows. So assuming that if we have some two derivations, 1 and 2 of the following judgment, that phi is just true, then we can consider that the derivations of the proofs are equal. Again, I'm intentionally sort of leaving away what I mean by equal or same or identical, whatever. But we'll, because now, let's say the system Lex doesn't have sufficient, let's say, the tools to actually like explicate more properly. But when we move forward to the Lex plus variant, where there's the propositional equivalence inside the language and the proof terms, we can make this sort of principle more explicit and actually even part of the language itself as a sort of a rule of the system.
Yeah, you go one slide back just for a second. Just want to.
Yeah.
Yeah. Okay. Thanks.
Yeah. No problem. So yeah, so that's the sort of irrelevance principle that this basic Lex system works with. Now, we talked about the sort of basic logical rules or operational rules. Now let's take a look at the substitution rules. This gets a little bit more tricky because we have three different types of substitution rules. They could be reduced, but at the cost of, let's say, legibility. So it's better to probably leave them as three separate kinds of rules. The first one is pretty much the basic substitution rule. The second one still behaves essentially as the basic one, with only the difference that now we are into substituting into propositions that are just true. However, the sort of the most tricky one and the interesting one is the third one, because for example, in the standard substitution, the substitution itself is typically defined by induction on the sort of the hypothetical premise, on the right hand premise. The same for the substitution in the second case. But in the third case, the substitution free, actually, to define this kind of substitution, we have to run or define it by induction on the first premise. Like there is, or put it in different way, essentially in the substitution rule 1 and 2, when we are defining the substitution, we rather care about the sort of shape of the whole we are substituting into, while in the case of the substitution free, we don't really care that much about the shape of the whole, but rather the shape or the structure of the thing we'll be substituting into it. And it's mainly caused by sort of the special behavior of the triangle modality, and when we are trying to eliminate it, and because it's restricted to the just true judgments. So there's sort of different reasoning principle applied when we want to define the substitution when we are substituting just true judgments into other just true statements. Now about some basic properties. We can prove exchange, weakening, contraction in this system. We can go forward. Again, we can also prove the following three substitutional lemmas corresponding to inference rules. And it's just sort of just capturing on the meta level what the rules showing there in a way of validity. I think we can also skip through this. So what's also worth pointing out that in this basic variant of Lex systems, both two connected, the implication and even the triangle modalities sort of prove theoretically well behaved, in the sense that we can establish harmony between the introduction and elimination rules, or in other words, that we can sort of define reduction and expansion rules that are exhibiting possibility to either sort of remove unnecessary detours constituted by sort of consecutive introduction and elimination, or sort of we can expand the sort of the derivation to show that the rule of elimination is not too weak. So for example, here's a derivation, here's the sort of the reduction rule for the sort of newcomer on the scene, the triangle modality. So essentially what's happened here, at first we have to sort of introduce the modality by the triangle introduction rule. Again, I'm reverting here back to the meta variable star, so we can sort of do it at the same time for both the true and just true variants. So we introduce it, then we eliminate it immediately afterwards. So we are sort of creating the necessary detour, and then we can remove it by this reduction rule, which sort of is essentially just application of the crucial substitution of the third kind that we just defined, and we construct the sort of the reduced derivation, and this reduction can then serve as a weakness for the fact that the elimination rule for the triangle modality is not too strong, that it doesn't allow us to like introduce new information by just introducing and eliminate it immediately afterwards. Just a brief example for the expansion. The idea is roughly the same. We want to first show that we can sort of remove sort of detours. Now we want to show that we in a way can introduce detours that doesn't also cause any like problems. So here we have starting with some derivation d of the triangle 5. Again, the variant starts, we can be both true or just true. Then we eliminate it. And then even after elimination, we still have sufficient information to reintroduce the existence modality. So it sort of shows that, again, the elimination rule is not too weak that it sort of preserves all the information needed to get back to the original derivation. So this sort of, to use sort of Penning's term, shows that the elimination rules are both locally sound and locally complete, or in other words, that they are in harmony, and thus sort of prove theoretically well behaved. Now, just for example, some propositions that can be proved in the system. Pick these three because they'll become useful later. The first proposition, that's mainly interesting the direction from right to left, because it will become quite handy when we'll be exploring the connection between our system of Lex logic to the propositional Lex logic. So, but this is just sort of a brief note, but we'll get to that more into detail later. The second proposition that's interesting that in this system we have sort of bidirectional distributivity. So not only the triangle distributes over implication, but we can also go into other direction. It's sort of take the modality and pack it back and put it in the front of the bracket. And the third proposition in a way shows that sort of the repeated applications of the modality can be in a way reduced or doesn't really get any new information. So again, these are just sort of prepared as a useful means for later. Now, just for a brief example of, for example, the proof for the proposition 1 and right to left direction, so we could get better just sort of taste of how the system looks in practice. There's nothing too surprising happening here. Only here I might just point out in the last step that we really need, for example, the J variant of the introduction rule, because otherwise there wouldn't be any other possibility to obtain just basically without the J variant, without the proof irrelevant variants to obtain this conclusion. So really the move from assuming phi that we can derive psi is just true, that we can sort of turn it directly to just true implication is crucial. By the way, here I'm sort of using a simplified notation where if the true is missing completely, it means it's sort of implied. If it's just, it means it's just true. So whenever there's missing the true, it's being just true there. So it's just to shorten the proof so it can fit on the slides, and it's much more readable this way. Now, so this will be sort of the basic overview of the logical variant. So now let's take a look at the more interesting computational variant Lex plus. That briefly we can think about as the Lex system extended with propositional equality as an additional logical operator. But furthermore, we also sort of throw away the sort of less informative logical judgments of phi true and phi just true, and instead we'll work with the new sort of typing judgments. The phi true will be replaced by T:(I), sort of more standard typing judgment that you would expect, but we also introduced a new one, the E triple dots phi, will be representative for the just true variants. As you might also notice, we now distinguish between terms and expressions. The idea is that terms are always linked to the proof relevant ones, while expression encompasses all the essentially the syntactic terms of the language. So all terms are expressions, but not all expressions are terms. And of course, even with this sort of explicit proof objects in the typing judgments, the informal meaning still remains same. The colon represents the idea it's true, and the triple dot represents the idea that there exists a proof of phi without caring about the structure. In other words, friendly equivalent. So now brief overview of the language. So first, let's look at propositions. So again, we retain atomic proposition, implication, and the modality. What's now new is the construct for the propositional equivalence. Essentially, it says to be used different equation. This is more sort of in the spirit of Martin-Löf. Essentially, it says that the terms or expressions E and E prime are equal, say, objects of the type phi. Now we have also the new class of terms, be representing the sort of proof terms, proof objects, whatever you prefer to call them. So we have variables, then constructor and eliminator for implication, and the lambda extraction and application. Then in the sort of this square bracket, the sort of angle brackets, we have constructor for the triangle modality, reflection, that's the constructor for the propositional identity newly introduced, and peel is the eliminator for also the newly introduced propositional identity. And then we have the larger class of expression. First note that, again, every term is expression, but what's different is now the sort of the eliminator for the triangle modality is considered as an expression because it's sort of necessarily proof irrelevant. And then we essentially introduce new variants, all the constructors and eliminators from the term side, the proof irrelevant ones, we just consider them as a proof irrelevant variant. So we just add the letter J to distinguish them from the basic ones. So it's sort of not much elegantly, but we have to sort of reproduce them, copy them in this way to so it would work in the way intended. Now again, we start with two categorical judgments, which are now just with the explicit proof terms or expressions, can form hypothetical judgments again. Nothing too new here. Now, additionally, what's new here about is the following through judgments. And an additional new thing, for example, if I use the meta variable star, now I'll be using the symbol star, and still serves the same purpose. It's shown here. The star essentially you can replace it or instantiate it both with the colon for the proof relevant typing or the triple dot for the proof irrelevant typing. So it's a sort of a placeholder, meaning that this applies to both variants. Now, so let's take all the new judgments one by one. First tells us that in the context gamma, the expression E reduces to the expression E prime, is essentially corresponds to the reduction rules. When I talked about the harmony with the introduction elimination rules, this is our way to, in a way, recapture the reduction rules on the language level of the logic itself. The second one corresponds to the expansion rules. Again, it tells us that in the context gamma, and the expression E expands to the expression E prime. And the final one that tells us that the expression E essentially belongs to the set of reducible expression or is reducible. The main purpose for this, the last one, is for the proof of normalization that utilizes the sort of tight reducibility or compatibility method. And this is our direct variant for that. So this is its main purpose. Now, for simplicity, let's take the type variant of the rules. The hypothesis rules behaves as you would expect with explicit rules, just rule. Again, nothing too surprising here. Now, for simplicity, I present only the true variants now of the sort of the type theoretical variants of the introduction elimination rules for the connectives. Again, I think I'll skip the implication variant because everything is pretty much standard here. So we have constructors, eliminator up. Then we have computation rule specifying how sort of remove the detours, and the expansion rule specifying how to sort of construct how to construct expansions. And the up-C is essentially congruence or different for technical reasons how to sort of do some of the proofs to go through. So I'll skip to the next slide. This is more interesting because now we're dealing with the sort of the introduction and elimination rules for the triangle modality with explicit proof terms. So first we introduce sort of the angled brackets as a constructor for the triangle type. Essentially takes that if we have some sort of proof irrelevant expression E, we can sort of put it in a box and pretend that we in a way don't see into it. And then we construct the type triangle phi. Then we have the eliminator for it, which I call X. In a way, this you may be familiar with sort of the, like intuitively what this does is quite similar. This can be pretty much taken as a notational variant of the let constructor introduced by Moji, which in a way captures the idea of, let's say, sequential substitution or call by value in a way. So how it essentially works is we have this rule and how to evaluate the expression, the eliminator in the conclusion. You start by taking the T, then you evaluate it first. This is a big difference to other rules, and then only the result you substitute for the X in E. So this is sort of the extra step that's required there. And we actually see when we have the computation rule, there makes the appearance of the sort of double bracket substitution, which corresponds to the substitution of the third kind that I introduced in the logical variant, but I'll specify it a little bit later on the slides. But this is sort of the expression, and this is a substitution that's required when we're putting the proof irrelevant expressions into other expressions. And then we have the expansion rule again that shows us that the elimination rules are not too weak. Now we have the introduction, elimination, computation rules for the equivalence or equality rather. Here these are pretty much the standard introduction, elimination, and computation rules for propositional equivalence or identity you would find in constructive type theory or related networks, related frameworks. So first, if we have a term of type phi, we can sort of introduce constructor. Reflexively, this sort of stipulation that, of course, every sort of term should be in a way identical to itself. And we have its elimination rule, which briefly speaking says that when we have sort of some stipulated equality between two terms, t and t prime, we can eliminate it if we can show that the property gamma holds for the case when the term t is sort of identical itself. It sort of works as an induction rule because this is inductive type. All we have to do is show that the property holds for the constructor, for the reflector, and then once this is done, then we can eliminate it and assume that the property gamma holds for any other equalities constructed in the type, and then the computation rule. So skip some additional stipulation. We assume that the reduction relation, the right arrow, is all transitive and reflexive, and then we also introduce sort of multi-step reduction relation denoted by the asterisk. But what's more important, now we can sort of capture in the language itself the proof irrelevance principle, the fifth one. So now we can have the premises, which says that we have essentially two proofs of proposition phi, which are irrelevant. We don't care about the proofs. If that's the case, then we essentially stipulate that in that case, those two expressions, E and E prime, has to be equivalent. And this is what renders the idea that we don't, the sort of informal idea that we hide the structure or that we don't care about the structure into practice. Because now it renders if we have two proof terms of the same proposition, then we can apply the principle and render them equivalent. So they have all, in a way, become one and the same proof object because we cannot distinguish them anymore from, at least from the viewpoint of the propositional equality that's at play. Again, here are the sort of the typed variants of the substitution rules. Again, I'm using the same notation for the first two substitutions since they behave essentially the same, but the double brackets for the last one, the substitution free, because again, as I mentioned, its definition is more involved and has to happen on the left premise, in opposed to the right premise in the case of substitution 1 and 2. Yeah, I maybe forgot to mention it, but here it's anyway easier to see like why this even happens. Because if you look at the premises of the substitution 1, substitution t, like here you essentially want to substitute t into for the x in phi, sort of close it. But if you look at it, this seems okay because we have sort of proof relevant typing, colon, and proof irrelevant typing here as well. Again, here the same. You have the colon here, colon here. But here the problem happens because we have the sort of triple dot here, but want to substitute in a variable x that's just relevantly typed. So this is where the mismatch happens, and this is why we had to sort of look into E by running the induction on it and show that we can actually use this open hole for substituting, because the way that the way the irrelevant judgment was defined, because if you remember the rule just, it also, if we can prove that something is just true at some point, it had to be true first. So there had to be some structure in a way, and this induction on it, we can show that it we can actually substitute for it. But again, still we have to restrict the conclusions to be again proof irrelevant. So you can think about it that you have some sort of proof hidden in a box. You can sort of look at it when you try to eliminate it, treat it normally. But when you do all the logical operations you wanted to do with it, in the end you have to return back to the box and sort of send it back. So this is the general idea what's going on in the substitution 3, sorry, and again sort of echoed in the elimination rule for the triangle modality. So this is again the clauses for the defining this new type of substitution. I won't be going clause by clause, maybe just the first two to get example. So when we substituting if we actually term t for x in e, it reduces to the standard substitution. So this works fine, but then we have to sort of define the case by case what happens when we actually, it's not term but expression, and these are all the sort of additional expressions and the J variants of the constructors and eliminators on the place of the term we are substituting with. So this is just how to handle the sort of this new type of different working substitution. Now for the Lex Plus system, there are some desirable properties we can show you that it has the subject reduction property, meaning that we have sort of typing judgment, and we reduce the e, that we can also infer that the result will still retain the same type, and also the subject expansion, that also we can, from the sort of result of a reduction in the reduction itself, we can derive back what was the type of the initial expression. For the sake of time, I think I might skip this. There's a sort of example, for example, how the proof would go for subject reduction. We might return to it, but judging on time, I think I just skip it for now. Now, briefly about the proof, as I mentioned already, it uses the Type's reducibility method, also known as the methodological relations or predicates, used by Plotkin. So what's the crucial component here is the new judgment, as I already briefly talked about. So again, just to recall, it means that in the context gamma, the expression E, which is either type relevantly or proof irrelevantly, meaning using the sort of meta variable star there, it belongs to the set of reducible expressions R of type phi. And the idea is that we have to define essentially case by induction on the structure of the type, how it's supposed to behave, this new type, this new judgment, sorry. So we have base case for when we have atomic proposition, that's obvious. So I'll just focus on the second case for the new existence modality. So we go through the definition. It tells us that okay, we can claim this new judgment, right, that E essentially is a reducible expression. If first we can derive the expression. Second, if we can show that the E reduces the number of steps to some canonical value, because remember these angled brackets are the constructor for the triangle modality, and with the additional condition that the A inside the brackets has to be also has to already have the property R. So these in similar fashion continues the definition for the implication and for the propositional equality, and then these conditions are these new type of judgments are then used for the normalization proof. The structure of the proof, again, is very standard. It proceeds in two basic steps, two basic lemmas, the sort of existence of value. So we first want to show that if we have expression that belongs to that is reducible, that belongs to the set R, then there exists a canonical proof expression or value of V of type phi such that the E reduces to this value. This is very straightforward because if you remember, it was pretty much by definition, because we cannot like claim this or divide if unless this is fulfilled. So this is pretty much by definition the first lemma to be proven, and the second lemma, the fundamental lemma, is sometimes called. Then we have to show that if we have some typing expression, it's open variables, and if we substitute variables into those, if we substitute those variables with terms that already belong to the set R, then the result will also have the property that the expression belongs to the set of the reducible expressions R. And by putting these together, it then gives us the normalization result, because essentially it tells us that if we have the expression and we substitute it with reducible expressions, we obtain the typing judgments, and if we have the typing judgment going back to the first lemma, then we know that it has to lead to some canonical value in the end. Now, this was sort of the basic introduction of the systems themselves. Now let's take a look at the sort of its relations or links, connections to the pre-established modalities on the scene. So first, let's take a look at the truncation modality. Truncation is one of the fundamental concepts of many type of theories for essentially obtaining like some controlled proof irrelevance in what are otherwise very proof-relevant frameworks. For example, as I mentioned, homotopy type theory. Most often, it's treated as some sort of modality. Use simple box, but typically you can find brackets or sort of double vertical lines and similar. And what it does, it allows us to do arbitrary type, for example, phi, and turn it into so-called truncated type, box phi, which is in a way what is in this, at least in the terminology often used in homotopy type theory and similar, so-called mere proposition. And what is mere proposition? This is a proposition for which all proofs are considered equal. So this is in a way sort of a way to get around the very useful, but sometimes like too restrictive idea of the proposition as types. So in a way it says, okay, yeah, sure, all propositions are types, but we have also mere propositions, which are sort of behaving more as the traditional logician would expect propositions to behave, meaning they are just true or false. You know, you don't really distinguish between these different truths. And this is how we obtain the sort of the proof irrelevant reasoning back. You have this idea of mere propositions, and they can be, they have, again, just at most one, and all others are considered equivalent to it. Now, to take a closer look, for example, I mentioned the homotopy type theory, the propositional truncation, modality is defined, for example, in the sort of well-known homotopy type theory book, is defined via following three clauses. That for any judgment T con phi, we can introduce this new one, sort of bracketed T with box phi. Then we have clause B, so that B is a mere proposition, and we have some function from phi to psi. Then we can construct a new function G from box phi to psi. Second clause, and the third clause says that box phi is a mere proposition, sort of stipulation on the outset that happens. Now, we can actually show that all these three clauses can be rederived in the Lex Plus system. Specifically, the clauses A and B, of course, can be regarded essentially as a truncation, interaction, eliminations, truncation and elimination rules. So if you rewrite them, you obtain the following variants. So again, on the left side, corresponding to the interaction rule, on the right-hand side, corresponding to the elimination rule. And we can show that in the Lex Plus, we can actually derive all these rules, which are shown below. And as you can see, just sort of links correspond on a sort of naive level very much closely to the interaction elimination rules for truncation. So this draws quite close. What's important to mention here is there's still a little bit of disconnect, because again, there was the assumption that the psi has to be mere proposition on the truncation side. But here we, in a way, recapture the idea that the restriction has to be mere proposition by not as a sort of stipulation on the meta level, but via the proof irrelevant typings. Here, there's not a direct sort of correlates to it, but they do the similar job. So we don't have to sort of assume that phi is mere proposition, since we use sort of the irrelevant typing, so it's just true anyway, and just true means there's at most one proof object anyway. In other words, if there is a proof and there is another proof, they are all equivalent, so there's just one. Now there's just examples of the proofs of how to reprove the sort of the truncation rules in our system, or rather how to reprove the rules that would correspond to the truncation rules. Again, for the sake of time, I think I'll just skip it. Now, what's more interesting is the clause C, as I mentioned, was just mere stipulation that, okay, bottom box phi is a mere mere proposition. Sometimes we can encounter more sort of explicit approach that essentially replaces the C clause with the more explicit one, such as this. Essentially says that we have two proof terms of the type box phi, then they are equivalent those terms, those proofs. So again, this is already very similar to the propositional proof irrelevance principle. Again, and we can again show that actually this rule can be rederived in the Lex plus system. So again, we can just assume that we have the modalized statements, the triangle phi, and two different expressions for it, and then obtain the same result by applying the crucial proof irrelevance principle in this system and derive the conclusion. So in a way, we can all the clauses can be the specifying truncation can be rederived in our system, which suggests this sort of the truncation seems to rely heavily on the sort of underlying notion of existence or judgmental existence. Now, in the rest of the time, let's finally look at the correction to Lex modality. I'll try to speed it up a little so we have some extra time for questions. First, the Lex and Lex plus systems basic is quite directly inspired by the system of Fenwick and Davis. It was originally meant as a system for sort of judgmental reconstruction of modal logic. Formally speaking, the Lex and Lex plus is closest to the possibility and especially Lex logic. Actually, we can also show that our modality, the triangle modality, obeys all the Lex modality axioms. If you are not familiar with the Lex modalities, it's a very interesting one. I would definitely implore to look at the paper, for example, by Hartlem. There is very sort of fascinating mix between possibility and necessity modality. There's very many occurrences and applications. It's quite interesting one. So just briefly, if you look at the three Lex axioms, the first one is kind of trivial. We can see that we can immediately obtain this by the sort of introduction rule for the triangle. The second one, if you actually remember, that corresponds to the third propositions we talked about, meaning that sort of repeated applications of triangle can be simplified. So this corresponds to that if we sort of replace simply the circles by triangles. And the last one, cause 3, is proof on the following slide, but again, for the sake of time, I don't go through all the details of it, but again, it just sort of establishes that, again, even this sort of Lex principle holds for our existence modality as well. What's not that surprising from this respect is that if we consider a fragment, Lex minus of the system, and by Lex minus meaning we sort of forget all the just true variants, the proof irrelevant variants, and treat it just the system alone, it can be then translated into back into the Fenwick-Davis system for which I call the Lex logic, just Lex here. And there are following two sort of helpful lemmas. We can then establish the following result at the bottom, that we can really say that if we can derive the judgment that phi is true in the existence in the Lex minus logic, if and only if we can derive that phi is true, or rather its translated version in the Lex logic, and the same holds for the just true variant and the Lex variant. So if we sort of delete away all the talk about the J variants, the proof irrelevant variants, the system itself is very essentially the system of Lex logic. However, we can go a little bit further. As it turns out, we can actually all the J variants, assuming we put them back again, can be derived from the sort of the proof relevant variants. Only what we have to do is add the following either inference rule, which I call E, which allows us that from phi implies triangle psi, we can derive that phi implies psi is true, or in its equivalent sort of more axiomatic form, which can be obtained from the rule by introduction of triangle and then introduction of implication. And this then shows, once we sort of consider this variant of our system, that in a way we can consider the basic logical variant, meaning without the propositional equality and the explicit typing, because the Fenwick system doesn't have it, can be considered essentially just the Lex logic plus this axiom, the axiom E. And this is, as I mentioned, essentially the right to left direction of the proposition one we talked about earlier. So this is why it's crucial, because if we consider the axiom, it can sort of do all the job of all other rules, because we can rederive them. So it's a very nice simplification, and it also shows much more clearly like what type of system is this here. So now we see, okay, this is essential axiology plus this additional axiom. So since it's sort of more prominent role, let's take a little closer look at it. Like on the sort of most basic approach, if we take sort of a syntactic reading, we can think it as a rule that allows us to, in a way, pull the triangle modality from the consequent in the first implication and sort of pull it out in the front of the brackets. So one way we can look at it, or possibly we can also regard it as, in a way, sort of a stronger converse of the distribution law, where we don't require the first antecedent to be also sort of modalized. This is one way to look at it. And the other way, the sort of semantic reading, what the formula tells us, is that if phi implies that the existence of a proof of psi, then there also exists a proof that phi implies psi. Now, I think the better way is actually to sort of digest what this rule is trying to, or axiom trying to convey, is to use a derived formula, which I call EK, which can be obtained from E by applying distributivity to the consequent and then rewriting it by distributing it inside the bracket. So we obtain the following formula. And if you look at the formula itself, essentially tells us that, okay, if we have a function from phi to triangle psi, then we can, in a way, essentially keep or obtain the same function that still leads to triangle psi, but we can for free essentially add the triangle even at the antecedent of the second implication in the brackets. In other words, look at it, let's say, from a constructive point of view, it tells us like, okay, assume like what would be constitute a proof of this one. Like essentially to prove this, you would have to assume that you have some arbitrary proof for phi, and then you have to show some sort of transformation that would convert it into the proof of triangle psi. So essentially the proof starts with the pronouncement of assume we have a proof of phi. And of course, what happens here, you prove here with the proof we start assume we have a proof for, assume that we have a proof for, or assume rather that there exists a proof for phi. So, and this is where I think one of the better ways to understand this, why this axiom makes sense and can be justified, is because it shows the close relation between what actually happens when we're trying to prove implications in constructive viewpoint, because sort of the act of let's assume we have a proof for phi. You don't actually like know the structure of the proof. It's sort of arbitrary proof. You don't really care about the structure. You assume it's there, but it's really just arbitrary proof. It's not something specific you have at hand. And it's sort of exhibited in a way, because again, if you sort of modelize the phi by the triangle, it again says also we don't care about the structure of the proof. So in a way, assuming directly phi or assuming directly the sort of modelized phi doesn't add or rather remove any more unnecessary information, because the proof is still structureless in a way, because by assuming you have proof, you don't know what its structure is. Neither in the case that you assume it exists, still no sort of assumption deeper on the structure. And you can do it only if, of course, where the difference is negated is still by the fact that whatever you concluded from it, it's still just under the modality, because you still don't care about its structure in the end. So this is what allows you to make this move or connect the idea that assuming you have a proof or assuming there exists a proof for something is essentially conflate together. Only as long as the consequences also don't require the structure to matter. So, and this final takes us to the conclusion. So just a brief recap. So the main novelty of the Lex and Lex Plus systems that they allow the treatment of the judgment of the general forms. There exists a proof of phi, which in other systems are typically very common, but only in meta language. Rarely they are treated on the sort of object language of the system themselves. Furthermore, the link between the existence modality triangle and the truncation modality, which I used the box symbol for, suggests that the notion of truncation is very closely connected. Notion of judgmental existence. One may also say that rather than truncation is a way derived concept. On the or fundamental concept of existence. This then also opens sort of door to other similar investigations. For example, there are many, let's say, truncation modalities with truncation like flavor. For example, we consider Wittgenstein's sort of proposition modality for questions in terms of inquisitive logic. This behaves and was actually directly inspired by the truncation modality. So it'd be interesting to explore this angle, how the existence interpretation enters there. Or another quite truncation like modality is considered by Artemov and Popescu, and we introduce a sort of intuitionistic knowledge modality in the epistemic logic. It's also quite interesting. And finally, the link between the existence modality and the lax modality. It sort of served as a nice sort of vehicle to show that, or to sort of that made to reveal the importance of the E axiom, or the sort of the right to left direction of the initial proposition that could be derived by the rules. But as it turns out, if we adopt it as an axiom or a rule, we can derive all just two variants. So it can be sort of in a way considered as a characteristic axiom of the lax logic presented in comparison to the lax logic by Davies and Fenning. Yeah, so this is everything for me. So thank you very much for your attention.